Hi, this is lecture 7 for Chem 223. Today we will be talking about acids and bases. Of course, here I have a picture of some bases from baseball, and up here some bottles of acid that are very old, possibly used by a prospector. Today we're going to have another handout and a shorter lecture. I'm going to show you the handout here really fast. So this is an acid-base supplement. On the first page, it's just going to review with you how to calculate the pH of various solutions and different concentrations of strong base here. So go ahead and work through these problems. Again, these have an answer key that goes along with them. What you're going to do with this handout is work through this first page like normal. Then you may discover you've made some weird mistakes. And then on the second page, it'll explain to you how to correct those mistakes or how to correctly calculate the pH under those circumstances. Okay, if you have any questions about that, let me know. You will need to work through this whole handout. This one's actually a bit longer, so it's actually about 10 pages in total, including the answer keys. There's a first section, an acid-base supplement, and then down here, there is an acid-base review sheet that you will need to go through as well. All right, but before we get into any more lecturing stuff, I'm going to start with a great video of a baking soda volcano that I found off the internet this morning. I love it. This poor little girl. She falls over and that vinegar is definitely pouring out. Let's watch it one more time. Watch where this bottle pours. It pours right where she falls. All right. So, acids, if you remember, the Bronsted-Lowry definition of an acid is a proton donor. So acids give protons away. And we classify acids into two groups, whether they are a strong acid or a weak acid. There's a very clear distinction between strong acids and weak acids. The difference is that strong acids, when you put them in water, completely dissociate, whereas weak acids do not completely dissociate. They partially dissociate and exist in equilibrium with the dissociated form and the protonated form. So the equations for a strong acid and weak acid look like this. So for a strong acid, you have HA, where the A is the acid and the H is your proton, going to A minus plus H plus. And the weak acid equation looks fairly similar, except for the strong acid equation, you have a single arrow pointing to the products, whereas with a weak acid, the arrow is going both ways. So the HA dissolves into the A minus and the H plus, but sometimes those come back together to form the HA. And so you're getting all of these species present in water, whereas with a strong acid, you're just getting the conjugate base and the proton. Okay, so an example of a strong acid would be sulfuric acid. H2SO4, when placed in water, completely dissociates to give HSO4 minus plus a proton. And so H2SO4 never actually exists in water, but these two species do. An example of a weak acid would be HSO4 minus, which can dissociate to give you SO4 minus plus a single proton. But these species, when in water, can reform to give you HSO4 minus. So sulfuric acid, since it has two protons, when you put it in water, it gives up that first proton immediately, very quickly and completely. But that second proton, it'll give it away, but then sometimes take it back, and sometimes it'll give it away and take it back. So all of these species are existing in water. For bases, we have a similar situation, but it's the opposite. So according to Bronsted and Lowry, a base is something that accepts protons. And the difference between a strong and weak base is the same idea as the difference between a strong and weak acid. A strong base completely dissociates in water, whereas a weak base has incomplete dissociation. Now, most strong bases are just hydroxides, so a hydroxide or multiple hydroxides complex with a metal ion. So very common examples are sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide. You'll notice these guys down here each have 2 hydroxide groups on it. You can get more and more of that depending on the charge of your metal ion, whether it's a 1+, 2+, etc. All right, now let's get into calculating the pH of a solution. So if you'll remember from Chem 105 and 106, you calculate the pH of a solution containing a strong acid by just taking the negative log of the concentration of that strong acid. So what I have here on this plot, on the x-axis is the negative log, or sorry, is just the log of the concentration. So at -2, this means that our hydrogen bromide or hydrobromic acid has a concentration of 0.01 molar. At -3, that's a concentration of 0.001 molar. At -4, it's 0.0001 molar, etc. And you'll notice that as the concentration goes down, or rather as the log of the concentration decreases, the pH increases, and this gives us a linear relationship here. And the opposite is true for the sodium hydroxide. Since that's a base, the more concentrated it is, which is on the left of this plot, the higher the pH. But for both of these guys, as you change the pH, you get, or as you change the concentration, you get a linear relationship with the pH. And that's true for most of this region, but if we zoom in right here, where we get really close to neutral pH, you'll notice that these lines don't stay straight. They actually curve and hug the pH 7 line right here. Why is this? Well, let's think about it conceptually first. So let's say that we keep following this straight line for sodium hydroxide. And that would mean that if we have a concentration or a negative log of the concentration of -8, so that's say 1 × 10⁻⁸ molar sodium hydroxide, we put that in water, that would give us a pH of 6. So if we think through that logically, what I just said is if this linear trend remained, then we could add some small amount of sodium hydroxide to increase the acidity of our solution. And of course, that just doesn't happen. We don't increase the acidity of our solution by adding a base. So what we have to take into account here when we get really close to a pH of 7 is the autoionization of water. And I will show you how to do that on the next slide. And the handout that you'll be working through today also has problems related to that. All right, so but let's figure out what the pH is of a 1 × 10⁸ molar NaOH solution. We know a couple of things about this. We know that when we throw sodium hydroxide into water, it completely dissociates. So we get 1 mole of sodium for every mole of hydroxide that's formed. And so we know that the concentration of sodium resulting from sodium hydroxide is equal to the concentration of hydroxide resulting from sodium hydroxide. We also know that from the autoionization of water, when water autoionizes, that it splits into a proton and a hydroxide. That means for every water molecule that auto-dissociates, we get 1 proton and 1 hydroxide group. We also know that the total amount of hydroxide that's in our water now is equal to the amount of hydroxide we got from our sodium hydroxide, plus the amount of hydroxide we got from our water. The problem is we don't really know what this value for the autoionization of water is. We do know how much hydroxide was added from the sodium hydroxide. So what we're actually going to do is, if you look, these are both negative ions. We're actually going to come up here and take these values up here, or these equations or relationships, and switch from looking at the negative ions to the positive ions. And the way we're going to do this is, again, that for every mole of sodium hydroxide we add, we're going to get 1 mole of hydroxide, 1 mole of sodium. And so their concentrations are equal. And again, we're saying that every time water autoionizes, we get one hydroxide and one proton. So we can simply say that these concentrations are equal to these concentrations. Now, why is that important? And we know that the value for Kw is going to be equal to our proton concentration times our hydroxide concentration. And that is always going to be equal to 1 times 10 to the negative 14. Well, I should back up there a little bit and say that actually if you change the temperature of your water, or if you change the elevation, you actually change this value slightly. But for now, we're just going to assume that 1 times 10 to the negative 14th is close enough for all of these calculations. Okay, but we still don't know the amount of protons that are in there or the number of hydroxides. We know an expression that gives us the total number of hydroxides in there, and that's equal to the concentration of sodium plus the concentration of our protons from the autoionization of water. But now let me ask you this question. Are there protons coming from anywhere other than the autoionization of water? The answer is no. We're definitely not adding protons by adding sodium hydroxide to this, so all of the protons are actually coming from there. We're going to take this expression and we're going to substitute that in for our OH minus, and that's going to give us this expression where we have H plus times H plus plus sodium plus. A lot of pluses. All right, now we still have two values in here in this expression or equation. Do we know either of them? Well, we actually do. We know the value for sodium, right? I'm going to say this again. We added sodium hydroxide to this, and it dissociated to form sodium and hydroxide. We know that we added sodium hydroxide at a concentration of 1 times 10 to the minus 8th molar. And so if this guy is completely dissociating, we now know that the concentration of sodium plus in here is 1 times 10 to the minus 8th molar. We can substitute that into this equation. And now you'll see that we only have one unknown value, which is our concentration of our protons. And now we can solve this to figure out our H plus concentration, and then we can take the negative log of that value to get our pH value. So of course, the way we're going to have to do this is we're going to have to multiply through this H plus and distribute it in these parentheses, and then solve this whole equation so that it's equal to 0. And we'll get an equation that looks like this, where we have A times H plus squared plus B times H plus C equals 0. And then we will use the quadratic equation to solve for our H plus concentration, and then take the negative log of that value to solve for our pH. All right, go ahead and work through that worksheet. If you have any questions, feel free to reach out to me or lob a question to Learning Suite. All right, good luck.